right, next speaker this afternoon is Sean Lozano, who's joined us from Mount San Antonio College. Sean's been working with Sam, and today we'll hear about their project together, Stellar Forensics, tracing the properties of circumstellar material around type 1b supernova progenitors in binaries.
Thank you. Guests. Stars appear brightest when they die. And sometimes when a star dies, it goes with the. Now, we observe these star deaths, and we use spectra and light curves so that we are able to classify these supernovae. Now, a subset of supernovae have been shown to material. The origins of this circumstellar material can't quite be explained by our current stellar wind. And so we have ourselves a bit of history, and we are all detectives today, sort of a CSI circumstellar material. And so we are starting to ask ourselves, how does this circumstellar material originate around these the observations we can make here on Earth? So one of these supernovae where we have two different projected light curves for both shock cooling and for nickel decay. As we see, our objects fall on these lines, but instead fall somewhere in between. So we have to ask, what is it about this supernovae that is present that would cause the luminosity to be much higher? And so ask specifically type 1b supernovae that we spent the summer observing. And in this type of system, we have a donor star that is about to undergo core collapse and its accreting partner. As the star is about to die, its envelope expands and creates an equilibrium called a material is being attracted towards its accretor. As the donor continues to stellar envelope will start to transfer some on the creation material. So how do we well, that would help us to better understand. So so Mesa among factors, we have two different and the other we color coded. The innermost circle would be a 3-day orbital period. System. So now that we've discussed our system, take a look at some of the mass loss rates that we notice that there is a system of mass transfer indicated by the y-axis here, where we're looking at the solar mass transferred over per year, that gets kicked off and it remains constant. However, when we see a system with 1.4 solar mass accretor, we see that rates. And so now that we've talked a little bit about the mass loss density profile with star, to achieve that, we use this equation here, where we're looking at the circumstellar material density in regards to the radius of the system. And we see that we have the mass loss radial distance from the circus uh, because our plot up to that we when we look, which becomes more difficult. However, day orbital file, how does that help? So optical for this and as you value, which is essentially the effect. Interestingly enough, for solar mass sooner than we would with the 1.4 mass system. However, with a 10 solar mass system, the shock breakout would actually occur within the circumstellar material. So this would cause a much more energetic and luminous supernovae, which would actually have a longer duration overall. The big question, well, if thinking about very early on, we believe that due to some of our calculations that we picked out from some of the literature, we would actually see indications of shock cooling that would be picked up at about 5 days since the go back to that again. We see that our So I just want to is the driver of the creation of circumstellar material around these systems. When we have a low Roche low orbital period. On the other hand, when we do have higher mass companions, SM, see an enhanced mass, oh, that's due to, excuse me, an interaction. Contemplate how we would observe all this with using the optical depth idea. We have circumstellar material density actually affecting the observable interaction with more. Uh, Thank you. I estimate. Ooh, that is a really good question. I would like to go back if you allow me one quick. I- yeah. So it would be just this green line is mainly what we were hoping to try to. Okay.